Good morning, afternoon, evening. Welcome back to Magnetism Notes Part 2. When we last left off, we were looking at this sample problem where I found I had a magnetic force going down, a magnetic field towards the west, which gave me a velocity coming out of the page. Like with a lot of physics problems, it is really helpful to draw a picture of these kinds of problems first. But I run into an issue because I'm a terrible 3D artist and I don't know how to draw things coming out of the page. Luckily, there is a standard system used in physics for drawing magnetic fields, specifically things coming out of the page. So, arrows pointing up, right, up, down, left, right, those are all good and fine pointing. For things that are going into the page, we use what's called feathers. It is like if you shoot an arrow and it's flying away from you, all you can see are the feathers. When something is going into the page, it is either a circle with an X in it or sometimes a circle with a plus sign in it, some kind of circle and a cross. That is what's called the feathers for things going into the page. And when things are coming out of the page, it's as if that arrow is flying towards me or it's a bullet coming towards me. We refer to it as bullets. It is a circle with a dot in the center of it. So when I'm talking about or trying to draw magnetic fields, I can use arrows pointing in two dimensions, a feather, a circle with a cross in it for going into the page, and a bullet, a circle with a dot in it for going out of the page. So I can see that right here, a wire that is carrying a charge, it's got a current in it. On the left of the wire, the magnetic field is going into the page. So I show that with these feathers. On the right of the wire, the magnetic field is coming out of the page. So I show that with these bullets. An electric current can temporarily induce a magnetic field in a non-ferromagnetic material like a copper wire. Why could it do that? Well, everything's about moving charges. So I have moving charges here in the current. Moving charges can help align those electrons, the electric domains within the material around it, and create a temporary magnetic field. If I have a wire in a loop, let's just imagine this for a second. Here's my wire that's in a loop. On the inside, I've got 4 feathers. On the outside, I've got 4 bullets. Everything matches up, but the inside is a much tighter space. There's not as much room to have those 4 feathers, so they are more highly concentrated than on the outside. That means inside of this loop, the magnetic field is going to be stronger. So if I keep looping more wire, then I'm going to keep increasing the strength of the magnetic field, and the inside is going to become a very strong magnetic field. A coil of wire has a special name. It is called a solenoid. It carries a current and produces a strong magnetic field because of all of those loops. Solenoids are really commonly found in doorbells and in car starters. An electromagnet, then, is a solenoid that is wrapped around a ferromagnetic core. So if you wanted to make your own electromagnet, you would need wire. The more wire you have, the better, so you can make more loops. Copper wiring tends to work well. A battery, the more voltage, the better. More volts means a higher current. And some kind of ferromagnetic core, like an iron nail. Electromagnets are used all over the place. They are very common. Motors, generators, transformers, loudspeakers, microphones, any kind of recording or data storage equipment like tape recorders, hard disks, MRI machines, industrial lifting magnets are electromagnets. Electromagnetic suspension, like with maglev trains. Electromagnets are everywhere. They are very useful. If I think back on part 1, the equation I used for the magnetic force was Fm is equal to QVB. But now I'm specifically talking about the magnetic force around a wire, and things are going to change a little bit. Current, which is measured in amps, and remember is the letter I, is a bunch of moving charges. I has a Q kind of embedded in it naturally. Current is moving charges, Q is charges, so those line up. I've still got the same B, and in order to make this Q and I work well, I need my velocity to become a length. We aren't really concerned about the speed of moving charges in a current, but the length makes these two equations work and be the same. So the force, magnetic force in a wire is equal to the magnetic field measured in Tesla times the current times the length. Sometimes it's written as a capital L, sometimes as a lowercase cursive l, whatever it takes for you to be able to distinguish the L from the I for current. So if I'm looking at this sample problem, I've got a straight wire carrying 5 amps of current. That is my I. In a uniform magnetic field oriented at a right angle. Remember, when things are at a right angle, you have the highest force, and it makes things easier if I think back on that right-hand rule. When 0.1 meters of wire is in the field, that's my L, the force is 0.2 newtons. So for my equation, F equals BIL, I've got my F, I've got my I, I've got my L. I can rearrange to solve for B, the magnetic field. I mentioned in the last video that there are 2 right-hand rules. The second right-hand rule is a little bit easier, in my opinion. It is figuring out the direction of the magnetic field based on the current in a wire and the direction that the wire is coiled. The way you figure out this one is by giving a thumbs up. Your thumb is pointing in the direction of the current, and the way your fingers wrap show the way the magnetic field is looping around the wire. So if I go back and look at this first example I had the current was flowing down. We said it's coming into the page left of the wire and out of the page on the right of the wire, and it's going in, looping, and coming out. This works with your right hand only. It's called the right hand rule for a reason. So if I had a current that was pointing up, it would be going into the page, looping around, and coming out of the page on the other side. So that is the second right-hand rule. To compare magnetism with electricity, here are some things to remember. Both of them, opposites attract, like things repel, whether it's a positive and negative charge or a north and south pole. We've got like charges or like poles repel, unlike charges or unlike poles attract. You can have an electric monopole. You can have something that is just positively charged without any negative charges. You cannot have a magnetic monopole. You will always have a north and south pole together. Electric field lines flow from positive to negative. Magnetic field lines go from north to south. The density of lines, how many field lines there are, is equal to the strength of the electric field or the magnetic field. For electric fields, we use amperes, amps. For magnetic fields, we use Tesla. And for both of them, the field can exert a force on a charge given in those equations. And that's everything you need to know about electricity and magnetism. Enjoy your evening.